Over the last few lectures, we have made quite a lot of headway in the theory of the representations of the symmetric group Sn. One of the major tools that we used there was this theorem due to Frobenius, which allowed us to calculate the compound character of a group starting from the irreducible representations of the subgroup. In particular, if we use the identity representation for the subgroup, we arrived at a particularly simple formula for a compound character corresponding to a given class, the nth class, and the formula for that turned out to be G over H times HL over GL, where G and H are the orders of the group and the subgroup, respectively. GL is the number of elements in the nth class of the group G, and HL is just the number of these elements which survive as members of the subgroup capital H. Now, we also saw in the last lecture that we could use this simple formula to provide to us enough compound characters to completely build up the character table for the group Sn, and for that we made use of this series of subgroups. Each partition of the integer n, each partition lambda, consisting of the integers lambda 1, lambda 2, lambda 3 up to lambda n, gave us a subgroup called H suffix lambda, which is given by S lambda 1 direct product with S lambda 2 direct product with dot S lambda n, where the S lambda i's are basically subgroups which only permute lambda I elements among themselves. So this particular subgroup is one in which the first lambda 1 elements are permuted among themselves, the next lambda 2 are permuted among themselves, and so on. We have seen that using elementary results in group theory, we can write down a complete formula for this compound character. So the compound character corresponding to the class labeled 1 to the alpha, 2 to the beta, and so on, that is labeled by the cycle structure as having alpha 1 cycles, beta 2 cycles, and so on, is given by this sum of these multinomial coefficients alpha factorial divided by alpha 1 factorial, alpha 2 factorial, dot alpha n factorial times beta factorial by beta 1 factorial, beta 2 factorial, dot beta n factorial, and so on. The one thing which makes this sum not so easy to use, at least not completely trivial to use, is that what we need to do is figure out the values for alpha 1, alpha 2, beta 1, beta 2, and so on, which are actually non-negative integers which satisfy certain constraints. All the alpha i's have to add up to the total number of 1 cycles alpha, all the beta i's have to add up to beta, and so on. And also, since you are talking of alpha 1, 1 cycles, beta 1, 2 cycles, gamma 1, 3 cycles, etc. inside S lambda 1, they must satisfy alpha 1 plus 2 beta 1 plus 3 gamma 1 dot equals lambda 1, and so on, right down to alpha n plus 2 beta n plus 3 gamma n and other terms equals lambda n. Now, it is a fact that you have to adhere to these constraints and find all possible solutions to these constraints, and only then use this sum that makes using this formula slightly difficult. But we found a way out in the last lecture by using the so-called symmetric polynomials. The symmetric polynomial corresponding to the class with alpha 1 cycles, beta 2 cycles, and so on is the product S1 to the alpha, S2 to the beta, and similar products multiplied together, where Si is a basic symmetric polynomial. It is the sum of the ith powers of each of the x's involved, x1 to the power I plus x2 to the power I, all the way up to xn to the power I. We use our permutation notation, sum over p x1 to the alpha, to denote this. The idea here is that we are going to carry out all possible permutations on the indices 1, 2, 3, 4 up to n, and only consider the distinct terms that come out of this. So, despite the fact that several permutations will give us x1 from x1 over and over again, we will only count that once And similarly, we will only count x2 to the power I once, x3 to the power I once, and so on. So this is our symmetric polynomial Si. Now the other important unit in this result that we are talking about is that corresponding to each partition lambda, which in turn corresponds to each irreducible representation of the symmetric group, we are going to have a term which is like x1 to the lambda 1, x2 to the lambda 2 up to xn to the lambda n. And this is again a symmetric polynomial because we are actually going to sum over all possible permutations of the indices 1 to 3 up to n, and once again only consider distinct terms that come out of these permutations. And it is easy to see that you can write our symmetric polynomial corresponding to class L, SL, which is, let me remind you, S1 to the alpha, S2 to the beta. If L has a cycle structure 1 to the alpha, 2 to the beta, and so on, can be written down as a sum of these symmetric polynomials over every partition, and the coefficients in this case are exactly what these compound Frobenius characters corresponding to the class L is going to be. The coefficient of the sum over all permutations of x1 to the lambda 1, x2 to the lambda 2 up to xn to the lambda n is going to be the character corresponding to this Lth class corresponding to the representation labeled by the partition lambda. Now, what we had shown is that the SIs, S1, S2, S3, etc. are functionally independent, and which immediately implies that if you consider the vectors formed by psi lambdas, taking all the class values one after the other, these are going to be linearly independent vectors exactly equal to the number of irreps that we have, and so they have enough information to give you all the simple characters. And in the last class, we saw how we could actually get the simple characters from these compound characters by writing a simple program. However, an important question that could arise is the following. Can we somehow modify this approach so that instead of getting the compound characters first and then reducing them down to the simple characters, can we get the simple characters directly? And the answer to this question happens to be yes, and that is exactly what we are going to describe in today's lecture. And our starting off point will actually involve the construct that we used to prove that the SIs are functionally independent. If you remember, in the last lecture we carried out this proof by determining the Jacobian of the transformation from x1 to xn onto the polynomials s1, s2 up to sn. And the Jacobian turned out to be n factorial times a completely antisymmetric polynomial involving the variables x1, x2 up to xn. Namely, it was the product x1 minus x2 into x1 minus x3 dot 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 x1 minus xn times x2 minus x3 dot 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 x2 minus xn up to xn minus 1 minus xn. Now, this is the construct that we are going to start our discussion with, because that, when combined with these symmetric polynomials, will give us the approach towards calculating the simple characters directly. In the long run, we will see that this leads to a rather nice graphical representation of the process, and that is exactly where young tableaus come in. Now, the Jacobian that we have mentioned was, apart from factorial n as a factor, the product of xi minus xj, where I and j both ran from 1 to n, with the condition that I is less than j, so that you don't get any repetitions. We are going to start with exactly this product of xi minus xj's, with one small modification. For most of this work, you will not necessarily need all of the n variables to be involved. If you are considering the character corresponding to a partition which has only m pieces, you will only need m of the variables x1, x2 up to xm. And that is why we are going to talk about a generalization of that particular Jacobian, a very simple and trivial generalization, d of x1, x2 up to xm, which is the product of xi minus xj for I less than j, with I running from 1 to m minus 1 and j of course running from 2 to m, with the expanded form given here. And as you can easily see, one term in this product is going to be the one which you get when you take x1 from each of the factors in the first row. That will give you n minus 1 powers of x1. Then you can take m minus 2 powers of x2 from the next row all the way down to 1 power of xm minus 1 from the last row, which of course leaves you with no powers of xm at all. Of course, this is not the only term that goes into this determinant or this quantity d. You actually have many more terms. But given the fact that this is a completely alternating function, that is, if you were to interchange any two of its variables, this is going to change sign, this one first term is enough to tell you exactly what all the other terms are. Indeed, this total antisymmetry makes it obvious that every one of these variables x1, x2, right up to xm, which appeared in a given term, must have different powers. For if they had the same power, then interchanging them would not have led to an overall change. But you must get a minus sign when you interchange two variables. So each and every one of the terms which go into D ultimately must be of this same form as the one here, except that instead of the order 1, 2, 3 for the indices here, you may have some other permutation. In fact, we should be able to get all the terms by permuting 1, 2 up to m of these labels in this way, and these terms will come with either a plus sign or a minus sign according to whether the permutation is even or odd. That means whether it takes an even number of interchanges to go from the original term 1, 2 all the way up to m to this particular order. So finally, we can write the expanded version of d x1, x2, xm as sum over all permutations delta p times the permutation operator acting on x1 to the power m minus 1, x2 to the power m minus 2 all the way down to xm to the power 0, where delta p is the sign of the permutation, plus 1 when the permutation is even, minus 1 if the permutation is odd. The way in which we are going to use this alternating function d is the following. We are going to take the symmetric polynomial s sub l corresponding to a class L and multiply that by d. Now, this of course has to be an alternating function as well. If we were to interchange any two variables, say xi and xj, in this expression, SL will stay the same, being symmetric, whereas d is going to change sign. So overall the product SL times d is going to change sign. Because this is an alternating function, it must have distinct powers for each one of these x1, x2, xn. So this will constitute of sum of monomials of the form x1 to the new 1, x2 to the new 2, all the way down to xm to the new m, where all of these new i's must be distinct. And because of this alternating property, we can get terms by simply permuting the indices 1, 2 up to m as with d, and that is why we can always decide to put the terms in these monomials in descending order, or other terms that are there in this SL times d can be found out by just permuting the indices. Now, let me point out that in d, if you take any one of the terms and add up all the powers of x's, you are going to get the sum of the integers 0, 1, 2 all the way up to m minus 1, and that is m into m minus 1 by 2. Now, if you did the same thing with SL times d, you are going to get an additional power of n coming from the SL. Therefore, each and every one of these terms that we are talking about in SLD must have powers of x which sum up to m into m minus 1 by 2 plus n. And as we have just said, we are going to put them in descending order for a typical term. And therefore, we can always write these terms as the operator p acting on x1 to the power lambda 1 plus m minus 1, x2 to the power lambda 2 plus m minus 2, all the way up to xn to the power lambda m. Here, lambda 1, lambda 2, lambda 3, all the way up to lambda m provides a partition of the integer n. Remember, these are non-increasing integers, and that is why, because we have already started with m minus 1, m minus 2, etc. for powers of x1, x2, xm, all these powers sitting here will be strictly decreasing. That is just what we want. Now, after you permute all of these indices together, you add them up. That's what the sum over p is telling us, but with a weighting factor which comes from the sine delta p of the permutation. Now, what we are claiming is SLD, this completely antisymmetric function of x1, x2 up to xm, must be the sum of such permutations and will have chi lambda L as coefficients, where this final sum is over all possible partitions lambda of n. Now, it is easy to understand that these coefficients that we have here, chi lambda L, must be linear combinations of the chi lambda L that we had written down earlier for the expansions of SL in terms of the symmetric sums over partitions. Well, what makes this really important is the claim that the chi lambda above, that is chi lambda L1, chi lambda L2, chi lambda L3, running over all the MC classes of the group Sn, actually give us simple characters for Sn. Now, the proof of this is actually rather non-trivial, and we are going to talk about that, but perhaps in a later lecture. Right now, what we are going to do is take this statement as a given that if you multiply the symmetric polynomial corresponding to a class L with this totally antisymmetric function d and expand that out in terms of these totally antisymmetric polynomials x1 to the lambda 1 plus m minus 1, x2 to the lambda 2 plus m minus 2, xm to the power lambda m, antisymmetrized over all possible permutations, then the coefficients are going to give you simple characters of the group Sn. Now, this sounds a bit complicated, and it is. So what we will do now is try to illustrate this formula and its usage through several examples. We will begin with a rather small group S3, for which we already know all the simple characters, so that we can easily check whether this procedure is really giving us the simple characters or not. And we are going to do the calculations by various methods. To begin with, we will do a full-fledged explicit calculation. Learning from that, we are going to try to see how we can speed up the job by picking up on trends that this explicit calculation is going to show us. So here is the calculation for S3. As you all know, S3 has three classes, and we are going to take the three classes one by one. So for class 1 cube, that is the class which has only the identity in it, 3 1 cycles, what we have to do is calculate S1 cube times d x1, x2, x3. And if I write this out explicitly, that is x1 plus x2 plus x3 whole cube times x1 minus x2 times x1 minus x3 times x2 minus x3. So let us now work this out step by step and do it in some amount of detail. First, what is this quantity x1 minus x2 into x1 minus x3 into x2 minus x3? D of x1, x2, x3, according to our notation. What we have just figured out a while ago is that this has to be the sum over all permutation of indices with the sign of the permutation multiplying that of the basic polynomial x1 square, x2 to the power 1, x3 to the power 0. Remember, it's x1 to the m minus 1, x2 to the power m minus 2, all the way down to xm to the power 0. And here we are using m equals 3 version of that. That's what the formula says, but what it really means can be easily figured out by actually multiplying this whole thing out or expanding out this formula. Of course, what this says, if you look at the pieces, is the following. One term is, of course, x1 square, x2 to the power 1 times x2 to the power 0. Now, the other terms can be obtained by permuting these indices 1, 2, 3. Equivalently, you could have kept the 1, 2, 3 fixed in place, but permuted these powers among themselves. That's what we are going to do. Note that 2, 1, 0 can be cyclically permuted to 1, 0, 2, and I'm putting 1, 0 and 2 on top of x1, x2, x3 here. Since a cyclic permutation with 3 objects is an even permutation, I get a plus sign. Another cyclic permutation will be 0, 2, 1. That's what gives me x1 to the 0, x2 to the power 2, x3 to the power 1. And then we come to the anticyclic permutations. Starting from 2, 1, 0, an anticyclic permutation will be 0, 1, 2. So we put 0, 1, 2 on x1, x2, x3 as powers. We put a minus sign for that. The other two are cyclic permutations of 0, 1, 2. And again, they come with a minus sign. Of course, if we drop the x3 to the power 0, or in general, powers of 0, we get this expression x1 square x2 plus x1 x3 square plus x2 square x3 minus x2 x3 square minus x1 x2 square minus x1 square x3. So that's what this expression, sum over all permutations with a weighting factor delta p of x1 square x2 to the power 1, x2 to the power 0 really means. So this is our d. What we need to calculate next is d times s1. Of course, what we really need is d times s1 cube, but we are going to do it in steps. So first, d times s1. S1, of course, is x1 plus x2 plus x3. So what I have done is I have basically taken this expression, which is d, multiplied it by x1 to get the first line here, multiplied it by x2 to get the next line here, multiplied it by x3 to get the last line. Now, when you do the individual multiplications, you can easily see that there are terms like x1 square, x3 square, terms with equal powers of two different x's. But notice that while you have x1 square, x3 square here, you actually also have minus x1 square, x3 square here. So they cancel. The next term that you get when you multiply x2 square, x3 here in d by x1, that is this term x1, x2 square, x3, also happens to have equal powers for two different x's, namely x1 and x3. And as a result, it must cancel with a term which comes with the opposite sign somewhere down the line. Sure enough, if you look hard enough, you get this term minus x1, x2 square times x3, which cancels this one out. Proceeding along these lines, we will see that most of these huge number of terms here cancel out and you are left with a rather small number of terms. x1 cube x2 plus x2 cube x3 plus x1 x3 cube minus x1 cube x3 minus x1 x2 cube minus x2 x3 cube. In fact, it will be easier to recognize the permutation involved here if I were to put in all the three variables x1, x2, x3 with their various powers here. This term, of course, becomes x1 cube, x2 to the power 1, x3 to the power 0. This one is x2 to the power 3, x3 to the power 1, x1 to the 0. Or if I am writing them in the order 1, 2, 3, this will be x1 to the power 0, x2 to the power 3, x3 to the power 1, and so on down the line. Now, once we have written down all the terms, it's easy to see that we can get all of these terms starting from this one by either permuting the indices 1, 2, 3 or just permuting the powers 3, 1, 0. So 3, 1, 0, the cyclic permutation gives you 0, 3, 1, which is here. Then another cyclic permutation gives you 1, 0, 3, and these are all even permutations. The odd permutations gives you 3, 0, 1, 1, 3, 0 and 0, 1, 3 respectively. So this, as promised, is actually delta p times the operator p acting on x1 cube, x to the power 1, x to the power 0. Summed up over all possible permutations, of course. And remember, if you had a look at our original D, that was x1 to the 2, x to the power 1, x3 to the power 0. And here we have x1 cube, x to the 1, x3 to the power 0. And that's sort of understandable, because here we are multiplied by s1. 1, the integer has only one partition, 1 plus 0. So this has added 1 to x1 square, or the power of x1 square, and given us x1 cube. And of course these two have not changed. Now, we can actually do this whole calculation a lot quicker if we forget about this explicit calculation and just looked at this formula. D x1, x2, x3 is just this particular sum over all permutations. So, when you multiply that by S1, which is just the sum over all permutations of x1, you get the following. Here I have again worked a bit explicitly, that is, I have shown this sum over p of x1 as x1 plus x2 plus x3. I have multiplied this by x1 to get this term, by x2 to get this term, and by x3 to get the third term here. Now of these, the last two terms simply drop out because you have equal powers of x1 and x2 in this term. So once you completely antisymmetrize this by summing up over all permutations of delta p times p acting on this, we are going to get 0. Similarly, this term has equal powers for x2 and x3, so this term will also drop off. So the only term that will be left is this, which is of course what we had here. Let us now move on to the next step. We are of course very far away from our final goal here. We need to multiply d x1, x2, x3 by s1 cube to at least figure out the simple characters corresponding to the class 1 cube. That is the identity class. But now, for s1 square, we proceed along the same lines. This actually was s1 times d x1, x2, x3. So we want to multiply that by another s1 again. So we can multiply this by x1 from the s1 to get this, by x2 from the s1 again to get this, and by x3 from s1 to get the final term. Now of these, the last term is going to just drop out simply because you have equal powers of x2 and x3 here, and as we have been saying, equal powers means after you antisymmetrize, it's going to vanish. So we essentially end up with two pieces. Delta pp, x1 to the 4, x to the 1, and delta pp, x1 cube, x to the 2. Remember, we have started out with x1 square, x2 to the power 1 in D. So this extra powers that we have got, these are the two possible partitions of the 2 here. Here we are talking about the partition 2, which is of course 2 plus 0, and so only 2 gets added to this power of x1. And here we are talking about the partition 1, 1 of 2, and that means powers of both x1 and x2 have gone up by 1. We need to carry out one more step, that's going up to s1 cube. And here, what we are going to do is we are going to simplify our notation a lot more. We will keep in the back of our minds that we have to antisymmetrize after taking all permutations into account, but we will not bother writing that down because we know that that's there for all the terms. We are just going to take a look at individual pieces, multiply them by the factors that can come from S1, and keep in mind the antisymmetrization possibility and just work from there. So, here, what we will have is the following. If we start from this term, x1 to the 4, x2, we can multiply by x1 to get this, x2 to get this, x3 to get this. Of this, the last one has equal powers of x2 and x3, and because of the antisymmetrization that we will have to do, this one drops out. So we will have just these two pieces. Of course, we don't have just these two pieces. We have completely antisymmetrized versions of these two pieces. Now, if you start from the other term that you already have, x1 cube x2 square, and multiply by x1 you get this, by x2 you get this, and by x3 you get this. Now this one is going to drop out because x1 cube x2 cube has equal powers of x1 and x2 and so can't survive the antisymmetrization. The important thing is I get x1 to the 4 x2 square in two different ways. One from this term by multiplication by x2 and again from this term by multiplication by x1. So in the final answer, this will come with a coefficient of 2. So putting all of these together, we get d of x1, x2, x3 times s1 cube. That's going to be this antisymmetrized polynomial starting with x1 to the 5, x2 with a coefficient of 1. Another starting with x1 to the 4, x2 square with a coefficient of 2. And the third one starting with x1 cube, x2 square, x3 with a coefficient of 1. And remember, we can easily figure out that these correspond to the partitions 3, 0, this one to the partition 2, 1, and this one with the partition 1, 1, 1, which is why all the three powers of x1, x2, x3 have gone up by 1 here, compared to d that is. Now this actually gives us our first simple character calculation. The simple characters for the class 1 cube corresponding to these three partitions of 3, 2, 1 and 1 cube are just 1, 2 and 1 respectively, just these coefficients that are sitting here. That was a claim in the theorem that we quoted, but we haven't proven, of course, as yet. And at least in this case, because we already know the simple characters corresponding to this particular class for various partitions, we can verify that this is actually correct. And not only that, the class 1 cube consists of only the identity and the corresponding characters are always dimensions of the representations involved. So these numbers 1, 2 and 1 are nothing but the dimensions of the irreps of S3. Again, something that we had verified a long time ago in group theory. And also in this series of lectures that we have on Sn, this was one of the first things that we calculated. So far so good, things are working out, at least in this particular example. Let's continue and try to get the full character table for S3 by this method. The next class in S3 is the class 2, 1. That is 1, 2 cycle and 1, 1 cycle. And for this we need S2, 1 times D, that is of course D times S2 times S1. Now D times S1 we already know, we have already calculated a while ago, and that's basically x1 cube x2 antisymmetrized. So when I multiply that by S2 square, which remember has x1 square plus x2 square plus x3 square, what I'm going to get is a sum of three terms. One, which I get by multiplying by x1 square, the antisymmetrized version of x1 to the 5 x2. Another, when I multiply this by x2 square, the antisymmetrized version of x1 cube x2 cube. And finally, x1 cube x2 times x3 square, antisymmetrized of course. Now here, we notice that first of all, this term is going to go away. If you antisymmetrize x1 cube x2 cube, you are definitely going to get 0. So we drop that. The other new thing that has happened here is that because we have jumped by powers of 2 this time, we have suddenly got a term which is really not in the right descending order, the one that we wanted from. Remember, all our partitions are labeled with corresponding terms here, but these terms must have descending order for the powers in x1, x2 and x3. But that's easily taken care of. All you have to do is realize that if you are completely antisymmetrized x1 cube, x2, x3 square, there will also be a term which has x1 cube, x2 square, x3. The same powers just permuted. But note that the permutation which goes from 312 to 321, what we really want, is an odd permutation. So you're going to get a minus sign. So once again, you can remember from what we had just done a while ago that this corresponds to the partition 3, that is 3 plus 0 plus 0 of lambda. This corresponds to 2 plus 1, that partition, and this corresponds to the partition 1, 1, 1. And therefore, for the 3 irreps corresponding to these 3 partitions, this class 2, 1 has characters 1, 0 and minus 1. Finally, we need class S3, which is D times S3. You're just going to multiply D, which is this x1 square x2's antisymmetrized version, by the symmetric sum of x1 cube, that is x1 cube plus x2 cube plus x3 cube. Firstly, I'm going to get x1 to the 5x2 by multiplying by x1 cube. Multiplication by x2 cube will give me x1 square x2 to the 4. Multiplication by x3 cube is going to give me x1 square x2 x3 cube. Now, in this case, the last two terms are not in the correct order. I want descending order in powers for x1, x2, x3 and so on. So, in this case, I want the powers to be 4, 2, 0, but we really have 2, 4, 0. So, to go from 2, 4, 0 to 4, 2, 0 via permutation, I need to switch these two, one interchange, odd number. Therefore, you get a minus 1 in front. So, this and this are exactly the same thing, but there's an extra minus because of the switch that we have carried out. Here, on the other hand, we have 2, 1, 3 as the powers, but we really want 3, 2, 1. Now, to go from 2, 1, 3 to 3, 2, 1, you have to switch these two to get 2, 3, 1 and then switch the first two again to get to 3, 2, 1. That means you need 2 interchanges. Even number, so you get a plus 1. So, here again corresponding to these 3 partitions, the coefficients are 1, minus 1 and 1. And using this, we can write down the entire character table for S3. Just take these numbers, 1, 2, 1 that we had already found out for 1 cube, 1, 0, minus 1 for 2, 1 and 1, minus 1, 1, what we had just found out for the class with a 3 cycle. So this is actually a set of simple characters that we have found out from S3 using our current approach, and you would all realize that this is our familiar character table for S3. So at least for S3, this method has worked out fine. I'm sure all of you would agree that working out the character table for S3 is hardly enough decompensation for learning all these rather complicated techniques. And you would be right. S3 has a simple enough character table that can be worked out by very elementary procedures, and we have already done that before. But just to show you how this actually works in more complicated scenarios, we are going to do this next for S4, of course, and then we are going to show you how we can replace much of the algebra by graphical techniques, which will help us to figure out the thing out for higher and higher orders. First, S4. And here, let me remind you that S4 has the following classes. A class with 4 1 cycles, that of course is the identity. Then there's another class with 1 2 cycle, 2 1 cycles. Another class here with 2 2 cycles. A class with 3 1 cycles and 1 3 cycle, 1 1 cycle. Another class with a single 4 cycle. The partitions are actually labeled in the reverse order using the same breakup. You have a partition of 4 into 4 alone. Then you have 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1, which I have written as 1 to the 4 here. So notice that we are going to write the partitions in the reverse order to the classes using the same breakup, and that's going to give us the character table in a rather neat form. Let us now move on to the next class, which is the class 2, 1 square. 1 2 cycle, 2 1 cycles. For this, we need to calculate ds1 square times s2. Thankfully, we already have ds1 square handy for us. We need to multiply this expression by s2. Remember, s2 is the sum of x1 square, x2 square, x3 square and x4 square. So now, by multiplying these by x1 square, x2 square, x3 square, x4 square in succession, this is what we are going to get. If I multiply this by x1 square, I get these powers 7, 2 and 1. By x2 square, I get 5, 4 and 1. By x3 square, I get 5, 2 and 3. Notice that because we are multiplying by higher powers now, that is, we are multiplying by squares rather than just first powers, what has happened is, although x3 had a smaller power compared to x2 to begin with, after the multiplication, x3 has gone up in power, so that this has come in the wrong order. Now, this is going to happen several times when you look at classes other than 1 to the n. In the class 1 to the n, the class corresponding to the identity, in this case 1 to the 4, the one which we have just concluded calculations for, at any given stage you are going to multiply only by a first power of x, so there is no possibility of a crossing of the powers. Here, such a crossing is very much possible. Now, these are the three terms you get from here. Of course, you don't get the fourth, which would have been x1 to the 5, x2 square, x3, x4. That term does not have to be written down because that will vanish after antisymmetrization. Well, if you did the same thing with this, x1 to the 4, x2 cube, x3, multiplied by x1 square, you get this, 6, 3, 1 for the powers. x2 square gives you 4, 5, 3. x3 square gives you 4, 3, 3, which of course goes away, simply because equal powers here. And x4 square now gives you a legitimate term, 4, 3, 1, 2 for the powers. But now notice that if you take this and this together, x1 to the 5, x2 to the 4, x3, and here you get 4, 5, 1. You have 5, 4, 1. Here you have 4, 5, 1. Same powers but in a different order. But this can of course be brought to the same term 5, 4, 1 by using a permutation. But that would be an odd permutation giving rise to an extra minus sign. So these two terms will cancel each other out. So finally this is what you end up with. 7, 2, 1. Whatever you have here with the coefficient 1. This term goes away. 6, 3, 1. Again with a plus sign. Now you have 5, 3, 2. That's the descending order that we are going to maintain. But 5, 3, 2 is of course not 5, 2, 3. It's the permutation of 5, 2, 3. An odd permutation, so you get a minus 1. And here you have 4, 3, 1, 2. But the descending order is 4, 3, 2, 1. Which you get with an extra minus 1 because of the single switch. And therefore, corresponding to these 4 partitions, all 5 partitions don't show up here. In particular, the partition corresponding to 5, 4, 1, or rather, once you take away 3, 2, 1, 0, the partition corresponding to 2 square, that's actually missing here. But all the other 4 contribute with coefficients 1, 1, minus 1, minus 1. So that will be another column of our simple character table, 1, 1, 0, minus 1, minus 1. 0 for the fact that you do not have a term corresponding to the class partition 2 plus 2. Now, the next class, 2 square. For that, we start with ds2 and then multiply by s2 again. Now, d, remember, was simply x1 cube, x2 square, x3. So, x1 square gives you 5, 2, 1. x2 square gives you 3, 4, 1. x3 square will give you 3, 2, 3, but that of course vanishes, equal powers. x4 square gives you 3, 2, 1, 2, and that also vanishes because of equal powers of x2 and x4. So finally we end up with ds2 in this form. The standard form with descending powers will be 5, 2, 1 with the coefficient 1 and all the corresponding antisymmetrized terms. And this one has to be put in the descending order 4, 3, 1 with one switch, and that's why you have a minus sign here. That's ds2. What we need is ds2 square. So we need to multiply this by s2 and this also by S2. So S2 of course means multiply by squares of x's. So x1 square here will give you 7, 2, 1. x2 square will give you 5, 4, 1. I've just written down all these terms explicitly. x3 square will give you 5, 2, 3. x4 square will give you 5, 2, 1, 2, which will of course cancel out because of the antisymmetry. What about this term? You are going to get 6, 3, 1 with a minus sign. The minus sign of course is just inherited from here. Then you will have 4, 5, 1 with a minus sign again. Then you will have 4, 3, 3 which will cancel out. And then you will have 4, 3, 1, 2. Now, let's put all of these together. You will get 7, 2, 1 with the coefficient 1. This corresponds to the partition 4. The partition 3, 1 will correspond to x1 to the 6, x2 to the 3, x3 to the power 1. This is of course here with the minus sign. Now this next partition, the 2 square partition, will actually contribute from this as well as this. Remember here, you do have a minus sign, but you also have the wrong order. To get this to the right order, you need to do a further flip of 5 and 4, and that means this will come with a plus sign again. The 2 together will give you a plus 2. And here, x1 5, x2 square, x3 cube has to be put in the descending order 5, 3, 2 with one switch, so minus sign. Here 4, 3, 1, 2 has to be put in the descending order 4, 3, 2, 1 with one switch. You had a minus, the one switch gives you another minus, so you get a plus 1. So the corresponding simple characters for these partitions turn out to be 1, minus 1, 2, minus 1, 1. So we are nearly done. Okay, we are 3/5 of the way done. Class 3-1. We start with ds1. Simple, the only term that you will get starting from x1 cube, x2 square, x3 is x1 to the 4, x2 square, x3. All the other terms, multiplication by x2 or x3 or x4, will give rise to equal powers and hence will drop out. Then we need to multiply by s3. That is x cubes. x1 cube will give you this, x2 cube will give you this, x3 cube will give you 4, 2, 4, which will drop out because of the antisymmetry and equal powers. And finally, x4 cube will give you 4, 2, 1, 3. So rearranging, if necessary, we get 7, 2, 1, no rearrangement necessary here, 1 with the coefficient. 5, 4, 1 with a minus sign. And here, 4, 2, 1, 3 has to be made into 4, 3, 2, 1. But to go from 4, 2, 1, 3 to 4, 3, 2, 1, you need to jump across twice and therefore you get a plus sign. So 1, minus 1, 1, these are the only non-zero coefficients. The other two are 0. So the column corresponding to this particular class in the character table will essentially have 1, 0, minus 1, 0, 1. So the final thing to calculate, class 4. That is, we are going to multiply d by s4, fourth powers of x's. This will give you x1 to the 7, 7, 2, 1 as you can see here. This one will give you 3, 6, 1. This will give you 3, 2, 5. And this will give you 3, 2, 1, 4. None of these will vanish. But if you want to rearrange them to the descending order, the standard order that we are using, well, this one needs no rearrangement. This one needs one switch to get a minus 1. This one, the 5 has to jump all the way to the front. So 3 to 5 will have to make 5, 3, 2. But that's a jump across 2 places, 2 minus signs. So plus 1 again. And here the 4 has to go all the way to the front, jumping across 3 places. So that will become a minus sign. So this gives us the final column of the character table as 1, minus 1, 0. Once again note that 2 square is not there. 1, minus 1. And this is your final character table for S4. With all this practice, we have enough under our belt to begin talking about the graphical method. where we are essentially going to do the same calculations that we outlined a while ago, but we will actually do that without having to write down a lot of powers of x and stuff like that. Today we are going to only talk about the graphical method for a single class of Sn, namely 1 to the n. Remember, that's a rather important class because the corresponding simple characters are nothing but the dimensions of the various irreps. So if you want to figure out the dimensions of an irrep of Sn, this is the approach that we are going to use. We will adapt this method for other classes as well later on, so that we can build up the entire character table, but that will take a bit of thought and we will leave that for the next lecture. But let me just show you what we did for 1 to the 4 in our example of S4. Let us look at one particular partition. Let's say the partition 2, 1 square, 2 plus 1 plus 1 for 4. And let's ask, how exactly did we calculate the corresponding simple character? We started from x1 cube, x2 square, x3 plus or minus terms with permutations. That's the anti-symmetrized version, which actually is D. Now what we need to do is multiply by S1, x1 plus x2 plus x3 plus x4, 4 times, because of what we need is S1 to the 4, and finally look for the coefficients of this particular quantity, x1 to the 5, x2 cube, x3 square, which is of course what you get when you start from this and multiply by x1 square, x2, x3. So these powers 5, 3, 2 are simply the power 3 that you already had plus the 2 which came from the partition, 2 that you already had here plus the 1 which came from the partition. 2 plus 1 gives you 3, and similarly 1 plus 1 gives you 2. Now at each stage of the multiplication, what we need to make sure is that the powers of two different xi's do not end up matching. Because as we have seen already, in any such case, the term will simply drop out. So what we are going to do now is essentially carry out this calculation without writing down all the powers of x's. We are just going to put in a dot for a multiplication by x1 in the first row of our graph, or a dot in the second row for a multiplication by x2, and so on. And what we have to do is making sure at no stage does the lower line have more dots than the higher one. Remember, we are starting with powers which go in a descending order 3, 2, 1. So if at any given stage the lower line has one more dot than the higher one, you're going to end up with equal powers. That's what we want to avoid. So with this restriction in mind, we are just going to denote the multiplications by dots. And let's see how that works. When you are talking of multiplication by S1, you can only put one dot in the top right here, this red dot. Remember, any other multiplication like 1 by x2 or 1 by x3, which would be signified by dots here or here, cannot lead to valid terms because they will lead to terms with the same power. And that has translated in our diagrammatic notation to the fact that when we build up this step by step, at any step we cannot have more dots in the lower line than the upper one. Well, the next step will be multiplication by another S1. Again, we will place dots, orange ones this time. But now you can place one dot to the right of this. This will actually signify multiplication by x1 square, which is a valid thing to do. And also, now that you have one dot here already, in the next stage you can put a dot here, because now you are not violating the rule that at no stage will the lower line have more dots than the upper one. So the orange dot can also go here. So you can have this or this. This, of course, is what you get when you multiply by x2. Of course, you have already multiplied by x1 once, and now you are multiplying by x2 to get this. Fine. What about S1 cube? I will put one more dot, a purple one this time. But remember, I cannot put a dot here any longer because you are not allowed to put more than 2, 1, 1. That's the particular partition we are looking at. So you are not allowed to multiply by more than x1 square. So a purple dot here will not be valid for this particular partition. But what we can do definitely is put a purple dot here. That is perfectly according to our rules. But starting from this, there are no other possibilities. You cannot put a purple dot here because then the third line will have more dots than the second line. On the other hand, if you start from this particular version, you can put a purple dot here, right next to this red dot. That will actually signify multiplication by x1 square x2. You can also put a purple dot here. What you cannot do is put a purple dot here because that would end up giving you 2 dots here compared to 1 on the higher line. So S1 cube essentially will give you these 3 possibilities. 2 dots already were there, you have put the third here, and here, starting with these 2 dots already, you have put the third dot here or down below here. Finally, we wrap up the calculation in this case by multiplication by a further S1. Now starting from this, it may look like the next dot, a blue one, can be placed here, but remember you can't do that. We are looking at the partition 2, 1, 1. So you can't put 2 in this row. So the only possibility is to put the blue dot here. Similarly, starting from this one, the blue dot can only go here. Starting on this one, the blue dot can go here. Another possibility would have been putting a blue dot right down here, but remember we are not looking at a partition which has 4 pieces. We are looking only at a partition which has 3 pieces. So this is where our distinction between M and N really comes in handy. You don't really need to x1, x2, x3, x4 for this calculation because you are specifically looking at a partition which has only 3 pieces. Only worrying about x1, x2, x3 will do. In the end, adhering to all these possibilities, you end up with this one possible, filling up of 2, 1, 1. Another one is here, another one is here. 3 distinct ways of doing this, and therefore, the corresponding character will simply be 3. This is really nothing but looking at 3 distinct terms that you get when you do the calculation, put them all together and get a coefficient of 3 in our expansion. Now, let us make a few remarks. Firstly, it's really not necessary to keep on writing down x1 cube, x2 square, x3 on the side. We already know that is always there. The other one is, it is a bit of a bother having to remember that you cannot put any more than 2 dots here, more than 1 here, more than 1 here at any stage because we are looking at the partition 2, 1, 1. So next step here is what gives us the thing that we have been waiting for a long time. This is where young tableaus come in. I'm going to formally define them in the next class, but today let's just take a look at what happens for this particular example. What you will do is start with the boxes where you are going to put the dots directly. 2, 1, 1. So 2 boxes on the first row, 1 box in the second row, 1 box in the third row. This way I know for sure that I will not overshoot and end up putting more dots in a given row than can be accommodated for this particular partition. The next change that I'm going to make is instead of using colored dots, I'm just going to use numbers 1, 2, 3 and 4. 1 will signify the choices when you do the first multiplication by S1, 2 when you multiply by S1 again, and so on. So here, let's do this in steps. When we multiply by S1, there's only one possibility. This corner box has to be filled up because you can't put a 1 anywhere else. If you did, you would actually end up with more dots in the lower row than in the upper row. What about S1 square? Now, the next dot, instead of writing it using a dot, I'm just writing it using the number 2. That can go either here or can go down below here. 3 can go in after this. From this, it can only go here. For this, on the other hand, it can go here or here. So at S1 cube level, we have three possibilities. 1, 2 and 3 here, and with 1, 2 down vertically, we have 3 here as a possibility, 3 here as a possibility. Finally, S1 to the 4, you had to add the fourth one. In fact, I don't even need to write that down because there's only one box left and that has to be filled up. And therefore, you have exactly 3 possible ways of doing it, and that is exactly why this corresponding character is 3, and therefore the dimensionality of this irrep, the one which corresponds to the partition 2, 1, 1 or 4, is exactly 3. These diagrams with boxes filled up with numbers is our first example of young tableau, which actually is one of the major things that we wanted to talk about in this series of lectures. There's a lot more to learn about these tableaux, and we are going to cover them in some detail in coming lectures. Remember, we have only worked out the approach towards the class 1 to the n so far. The approach for other classes will be somewhat different. So we will have to talk about that. Also, there happens to be a rather beautiful and simple to use formula called the hook formula, which will allow us to calculate the dimensionalities of the different representations directly from a single tableau, rather than trying to calculate how many different ways we can fill up the tableau with numbers. That is also going to be very useful. The hook formula happens to be a very simple one to state and rather astonishingly difficult to prove. So we are not going to bother with the proof or the exact proof of this formula. I will give you a hand-waving argument which shows why it should be true. But all that will have to wait for the next lecture. Bye for today.